Welcome to Introduction to Sedimentation and Stratigraphy. I'm Dr. William Patterson. Today we will be talking about deltas, parts 2 and 3 of 3, where we will discuss water depth and modification of deltas. A delta progrades by sediment accumulating on the seafloor at the delta front where it builds up to sea level. This increases the area of the delta top. For a given supply of sediment, the rate at which the delta progrades will depend on the thickness of the sediment pile that must be created to reach sea level. Delta progradation will hence occur at a greater rate if it is building into a shallow lake or sea, and the area covered by the delta lobe will be greater because it forms a thin, widespread body of sediment. In contrast, a delta building into deeper water will form a thicker deposit that progrades at a slower rate. A delta building into shallow water will tend to have a large delta plain area. If the climate is suitable for abundant plant growth, peat mires may develop on part of the plain away from the delta channels, and delta successions that have been developed in shallow water settings may therefore include coal beds. The delta front facies will all be deposited in shallow water and hence will be strongly influenced by processes such as wave action. Sandy and gravelly deposits are therefore likely to be relatively well sorted. Here we have a most amazing example of a Gilbert delta. In deeper water, a greater proportion of the sediment will be deposited in the lower part of the delta slope as a thicker coarsening up succession is generated during delta progradation. The area of the delta top will be relatively small, with less potential for the development of widespread fine-grained delta plain facies and mires. Wave reworked mouthbar facies will be limited in extent because of the small area of shallow water where the wave action is effective. The delta slope will be extensive and a potential site for gravity flows, where coarser materials may be mobilized to form debris flows, and finer sediment mixed with more water will generate turbidity currents. The lower part of the delta front may therefore be a site of deposition in these mass flow deposits that may extend out onto the basin plain. The combination of a supply of coarse sediment and a steep basin margin results in a particular delta form that is unlike all other deltas. These even have a special name, Gilbert-type deltas, named after the American geologist G.K. Gilbert, who was the first to describe these deposits in 1895. Gilbert-type deltas have a characteristic three-part structure: top set, foreset, and the bottom set. The top set, the delta top, is a subaerial to shallow marine environment with gravels deposited by braided rivers and in some cases reworked by wave processes of the shoreline. In front of the top set lies the foreset, also known as the delta front, which is very distinctive because the beds are at a steep angle, typically up to around 30 degrees, and close to the angle of repose for granular material. Deposition on a foreset occurs by two mechanisms: debris flows of poorly sorted gravel mixed with sand and mud, and well-sorted gravels deposited by grain flow or avalanche processes. Slumping is often seen on the delta because the steep slopes of the foreset can become unstable. At the base of the foreset, sloped sediments are finer, comprising mud, sand, and some gravel that lie approximately horizontally and are the products of turbidites and suspension deposition in a pro-delta setting. In this context, it's known as a bottom set. As a Gilbert-type delta progrades, the foreset builds out over the bottom set, and in turn, the foreset is overlain by the top set facies. The resulting deposit is in the form of a sandwich of steeply dipping conglomeratic strata between layers of horizontal beds of conglomerate and sandstone. The height of the foreset is determined by the depth of the water the delta is building into, and can range from a few tens of meters to over 500 meters. These thick packages of steeply dipping strata are unique to Gilbert-type deltas. The only deposits that approach this angle of deposition are alluvial fans, and these are at a lower angle than the 30 degrees recorded in Gilbert-type deltas. These are typically found at the edges of basins that have active faulted margins, such as rift basins, where the uplift of land at the margin creates steep topography that supplies gravel while the basin is subsiding to form a deep, steep-sided basin. The delta is regarded as river-dominated, where the effects of tides and waves are minor. This requires a microtidal regime and a setting where wave energy is effectively dissipated before the waves reach the coastline. Under these conditions, the form of the delta is largely controlled by fluvial processes of transport and sedimentation. The unidirectional fluvial current at the mouth of the river continues into the sea or lake as a subaqueous flow. The channel form is maintained with well-defined subaqueous levees and overbank areas. Bedload and suspended load carried by the river is deposited on the subaqueous levees, building up to sea level and extending the front of the delta basinwards as the strip of land either side of the main channel forms the characteristic bird's foot pattern of a river-dominated delta. A common feature of fluvially dominated deltas is channel instability due to the very low grading on the delta plane, resulting in frequent avulsion of major and minor channels. The course of the river changes as one route to the sea becomes abandoned and a new channel is formed, leaving the former channel. Its levees and overbank deposits are abandoned. Repeated switching of the channels on the delta top builds up a pattern of overlapping abandoned lobes. When a delta channel avulses, a new lobe starts to build out at the new location of the channel mouth. The abandoned lobe subsides by dewatering until completely submerged. So the water gets squeezed out and the volume of the sediment decreases, causing it to sink. Through time, the channel will eventually switch back to the position overlapping the former delta lobe. This results in a series of delta lobe successions, each coarsening upward. The deposits of river-dominated deltas have well-developed delta-top facies consisting of channel and overbank sediment. The characteristics of these facies will be essentially the same as those of a similar fluvial system. The overbank areas of a delta top may be sites of prolific growth of vegetation, leading to the formation of peat and eventually perhaps coal. The channels build out to form the toes of the bird's foot, between which there are large interdistributary bays. These bays are relatively sheltered and are sites of fine-grained subaqueous sedimentation. Crevasse splays from the distributary channels supply sediment into these bays and gradually fill to sea level, becoming the vegetated part of the delta plain. The filling of interdistributary bays results in a small scale, a few meters thick, coarsening up succession. In front of the channels, mouth bars form and are localized in areas in front of the individual delta lobes. Little redistribution of mouth bar sediments by wave action or tidal processes occurs, such that individual mouth bar bodies are relatively small. Waves, driven by strong winds, have the capacity to rework and redistribute any sediment deposited in a shallow water, especially under storm conditions. The river mouth and mouth bar areas of a delta are susceptible to the action of waves, resulting in a modification of the patterns seen in river-dominated deltas. Progradation of the channel outward is limited because the subaqueous levees do not form, and bedload is acted upon by waves as quickly as it is deposited. Any obliquity between wind direction and the delta front causes lateral migration of the sediment as the waves wash material along the coast to form beach spits and mouth bars that build up as elongate bodies parallel to the coastline. Wave action is effective at sorting the bedload into different grain sizes, and the mouth bar deposits of a wave-influenced delta may be expected to be better sorted than those of a river-dominated delta. Progradation of wave-dominated deltas occurs because the wave action does not transport all the material away from the region of the river mouth. A net supply of bedload by the river results in a series of shore-parallel sand ridges forming as mouth bars build up and out to form a new beach. Wave-dominated delta deposits display well-developed mouth bar and beach sediments, occurring as elongate coarse sediment bodies approximately perpendicular to the orientation of the delta river channel. This is in contrast to the river-dominated delta deposits that would be expected to show less continuous mouth bars and a high proportion of channel and overbank deposits forming the delta lobes. Delta front and pro-delta deposits may not significantly differ between these two delta types. Here we see a wave-dominated delta formed where wave activity reworked the sediment brought to the delta front to form coastal sandbars and extensive mouth bar deposits. Coastlines with high tidal ranges experience onshore and offshore tidal currents that move both bedload and suspended load. A delta building out into a region with strong tides will be modified into a pattern that is different from both river and wave-dominated deltas. First, the delta-top channels are subject to tidal influence with reverses of flow and or periods of stagnation as a flood tide balances the fluvial discharge. This may be seen in strata as reversals of paleocurrent indicated by cross-stratification and the formation of mud drapes. Overbank areas on the delta top may be partially tidal flats, and all of the delta top will be susceptible to flooding during periods of high fluvial discharge coupled with high tides. The tidal currents rework sediments at the river mouth into elongate bars that are perpendicular to the shoreline. These are modified mouth bars that may show bidirectional cross-stratification and mud drapes on the crossed bed foresets. This is due to the reversing of the ebb and flood tidal currents. And here we see a tide-dominated delta in a macrotidal regime that shows extensive reworking of the delta front by tidal currents and the delta top with a region of intertidal deposition. The deposits of tidally influenced deltas can be distinguished from other deltas by the presence of sedimentary structures and facies associations that indicate that tidal processes were active. These include reversals of paleoflow, mud drapes, and so on, with subaqueous mouth bars elongate parallel to the river channels. The overall succession of strata will display the characteristic coarsening up of a delta, a feature that allows it to be distinguished from other tidally influenced environments such as estuaries that have much in common in terms of depositional processes. The main distinguishing feature is that a delta is always a progradational feature, whereas an estuary commonly forms as part of a retrogradational or transgressive succession. When the channel on the delta top changes course, the former lobe is abandoned as a new site of deposition is occupied. River-dominated deltas tend to have the most frequent changes in position of the active lobe, but a avulsion of channel course also occurs in other delta types. The deposits of an abandoned lobe will gradually compact as water deposited with the fine-grained sediment escapes from the pore spaces and the bulk density increases. Essentially, we're squeezing all the water out of this clayey blob, making it more dense. This compaction occurs without any additional load and results in the abandoned lobe subsiding below sea level. The fall below sea level of the abandoned lobe will be accelerated if the delta is located in a region of overall subsidence or if there's a eustatic rise in sea level. The beds that mark the end of sedimentation on a delta lobe are known as the abandonment facies. In the upper part of the delta plain, these will be peats or paleosols that represent a low clastic supply to this part of the plain now that active lobe progradation has moved elsewhere on the delta. The fringes of the delta lobe will be areas of slow, fine-grained deposition in shallow water, while further offshore, carbonate facies may form over the toe of the delta. Abandonment facies may show intense bioturbation because of the slow sedimentation rate. After a number of changes in channel position, the active delta lobe may reoccupy an earlier position and prograde over an older, compacted, and submerged delta lobe succession. In cross-section, the result is one coarsening up delta lobe succession built on top of another. Repetition of this pattern has been recognized in the stratigraphic record, referred to as delta cycles, with each cycle representing progradation of an individual delta lobe. The thickness of a delta cycle will be controlled by the depth of water in the receiving basin, and may range from a few meters to tens or hundreds of meters in thickness. Variations on the idealized delta cycle are common. A complete succession from offshore fine-grained deposits up to the delta channel fill will be seen only at the point where the axis of the lobe has built out basinward. In other positions, the top of the cycle will vary from delta plain carbonaceous mudstones to interdistributary bay mouth deposits or mouth bar sands. In a hinterland direction, subsidence will not be great enough for fully marine conditions to develop at the base of each delta cycle, and therefore only the upper parts of the typical succession may be seen. The delta front is a slope that can vary from about 1 degree in mud-rich settings to over 30 degrees in coarse-grained deltas. Even the very low-angle slopes are potentially unstable, and mass movement of loose, soft sediment on the delta slope is common. Debris flows, slumps, and slides that consist of remobilized delta front deposits, reworked and remobilized, will occur and may be seen as part of the succession in deltaic facies. Slumps and slides can be large-scale, involving the movement of bodies of sediment tens of meters thick and hundreds of meters across. The surfaces on which the slides move are like faults, and these features are often regarded as growth faults, sedimentary deformation structures. Further instabilities also arise as a result of the relatively rapid accumulation of sediment on a delta. Coarser and relatively denser sediment of the delta top is built on top of muddy, wet, less dense delta front facies, and the result is the formation of mud diapirs. These deformation processes occur during the formation of the deltaic deposit, giving rise to some quite complicated sedimentary features within delta succession. Beds may be deformed on a scale ranging from slump folds a few centimeters across to sedimentary faults that rotate and displace packages of strata tens of meters thick. Similar features can occur in other depositional environments, but they're probably most common in deltaic facies, especially if the succession contains a high proportion of muddy sediments that deform relatively easily. The definition of a delta includes the concept of progradation. Deposition results in the sedimentary body building out into a lake or sea. The sedimentary succession formed will therefore consist of progressively shallower facies as the pro-delta is overlain by the delta front. which is in turn superposed by mouthbar and delta-top sediments. The succession formed by the progradation of a delta therefore has a shallowing up pattern, a series of strata that consistently shows evidence of the younger beds being deposited in shallower water than the older beds they overlie. In the delta front subenvironment, the deepest water facies, the pro-delta deposits, are the finest grains as they're deposited in the lowest energy setting. In a shallowing up succession, they will be overlain by sediments of the delta slope that will tend to be a little coarser, and the shallowest facies will be those of the mouthbars, which are typically sandy or even gravelly sediment. The beds formed by delta progradation will therefore show a coarsening up pattern. The shallowing up, coarsening up pattern is one of the distinctive characteristics of a deltaic succession, but it can be considered to be more diagnostic of a delta only if the top of the succession shows a transition from deposition in subaqueous to subaerial environments. Deposition on the delta top may be the recognition of a river channel, signs of plant growth and soil formation, or other exclusively subaerial physical, chemical, or biological processes, such as the desiccation cracks or tracks of land animals. One caveat must be added. A coarsening up marine succession capped by continental facies can be formed at a coastline where sediment is supplied by marine processes. So it's important to establish that there is evidence of a river or alluvial fan supplying sediment from the land if the succession is to be reliably interpreted as a delta deposit. When the channel on the delta top changes course, the former lobe is abandoned and a new site of deposition is occupied. River-dominated deltas tend to have the most frequent changes in position of the active lobe, but a avulsion of channel course also occurs in other delta types. The deposits of an abandoned lobe will gradually compact as water deposited with the fine-grained sediment escapes from the pore spaces and the bulk density increases.